And the last problem I want to do is problem 66 in chapter 5. This is a 3-dot problem, but in my opinion, parts A and B are more like, part A is more like a 2-dot problem, and part B is more like the 3-dot problem. Anyway, we're going to do everything the exact same way as before. Let's make a free body diagram. Start with M1. Block. And this is on flat surface, so gravity's pulling down. And gravity's pulling up here. And, sorry, gravity's pulling up. Gosh, what am I saying? Normal force is pushing up. We have the tension in the rope pulling this way. And we have a push force in the same direction. We'll just call it F. And before I continue, let me just draw a little sketch of the situation. Something like that, roughly. Let's define direction. We're going to go basically like that. So this is the negative direction. This is the positive direction. This is the negative direction. And this is the positive direction. Why did I add these little curves? Because this is at an angle, right? So up is positive, and so is up in this direction. So up in that direction is positive. Down is negative, and so is down to this direction. So down in that direction is negative. This direction going this way is negative, and this direction going this way is positive. So that's kind of why I made it all crooked like that. Alright, and now M2 over here. And we have a block looking like this, sort of. Gravity's going down. Normal's perpendicular. This is FG2, FG1, so we don't get confused. And tension is pulling up that way. And let's just quickly draw in our components, even though it's technically not part of a free body diagram. I like to get that out of the way initially. And which angle are we dealing with? Well, here's our ramp, right? Basically, this is theta. We do the same process I told you before if you want to do my method. And if you work through that, you should be able to figure out, I'll leave that up to you, that this angle is theta. It's horrible. Theta. Okay, and this is FGX and FGY. Now, what comes after the free body diagrams? You guessed it, net force equations. F net y equals 0. Why? Because it's on the surface and it's not moving up or down. This is the y direction. That's Fn1 minus Fg1 based on our positive and negative definition. And so Fn1 equals Fg1. And how does this help us with the problem? It helps us it absolutely does not help us. But I'm doing it just for consistency because eventually we're going to need this whole net force stuff because you're going to see that friction is related to net force. Start over. Eventually we're going to need this normal force stuff because, as we're going to learn, friction is related to the normal force. So soon these will not be useless. F net y equals 0, which equals F normal 2 minus FGY. So Fn2 equals FGY. Again, we don't need this in this case. Alright, what about x for this one? F net x equals. Well, in this one, all the x forces are going in the same positive direction, according to this diagram. And so we're just going to go F plus Ft. And in this one, also equals M1 A net. And I'm just going to lay it out. The acceleration of this block equals the acceleration of this block because they're linked with a rope. So I'm not going to call this like 1 or anything. Over here, F net x equals m2 times a net, which equals, we have gravity, the x component of gravity pulling down in the positive direction. So that's Fgx minus the tension going up in the negative direction. That's this. Okay, now it's time to plug in what we know. So M1 we know is 3 kilograms, so 3 kilograms right here times A, let's just call it A for now. That's going to equal, again, F plus Ft. Over here, mass 2 is 1 kilogram. Might as well not even write it, but just to make it as clear as possible. And Fgx is going to be Fg sine of theta. And so Fg is m2, which is 1 kilogram, times g, 9.8 meters per second squared, times sine of the angle, which is 30 degrees, minus Ft. We're looking for Ft. So what we want to do is, here's a little trick that if you don't know algebraically, this is a good trick to learn. If we have two equations and two unknowns, we also know F. Sorry, this is a 2.3. 2.3 newtons plus Ft. When we have two equations and two unknowns, in this case the two unknowns are A and Ft, this is the strategy I use. We're looking for Ft, so we want to get rid of A. And to get rid of A, we solve both equations for A and then set them equal to each other. That's how I do it. So let's divide both sides by 3 kilograms. So A equals 2.3 newtons plus Ft over 3 kilograms. And over here, this is just 1, so I'm just going to write A equals 1 times 9.8 times sine of 30 is 4.9 squared minus Ft. This is a 2. So let's set these equal to each other. A equals A. And let's do it on the next page. Let's do it on this page. Let's do it over here. Let's do it down here. Let's do it over here. 2.3. Let's do it in a different color. (2.3 n plus Ft over 3 kilograms equals 4.9 meters per second squared minus Ft. Multiply both sides by 3. Solve. Multiply both sides by 3. Combine the Ft terms. Combine the numbers. Kilograms times meters per second squared turns into a Newton unit, and you get Ft equals 3.1 newtons. I skipped a bunch of algebra. You guys are good at that by now. If not, worry. Cool. Okay. So this to me is a 2 dot problem. It's a little tricky, but not that bad. Part B though, woo. Well, let me explain part B before I switch and actually do it. Part B, they're saying what excuse me, what force, pushing force here, F, is necessary Um, or no, what's the largest value of the pushing force you can have? Excuse me, without the cord becoming slack? Well, there's no friction here, so first we have to wrap our minds about what that means. If there's no friction, there's nothing preventing these blocks from sliding. And so what's going to cause these blocks to slide is, well, this pushing force, but also gravity pulling down. Now, as long as your pushing force is less than or equal to gravity pulling down, this rope will be tight. Right? Think about that. You should be able to visualize making this ramp in real life and doing that. As long as you don't push harder than the force pushing down here, the rope's going to be tight. As soon as you push harder than gravity's pulling down, this box is gonna accelerate more quickly than this, which is going to cause it to get closer to this one, which is going to cause the rope to get loose. That is what's going on. So when it asks, what is the maximum push force before the rope becomes loose? That's when your push force would equal the force of gravity going down. So let's do that on the next page. And that's conceptually what's going on. Physically, mathematically, we have to use the equations we were originally given. So the net force equation on block 1 was just m1a equals ft plus f. And so when, by the way, when your pushing force equals, let me go back to this picture, when your pushing force, pushing this block, equals the force of gravity pulling this down, which is Fgx, by the way, the rope is loose, right? Because these blocks are accelerating at the same rate. To me, it's just like free fall in a space shuttle. Or think of it this way: if you're in an elevator and the rope gets cut in the elevator, you are falling at the same rate as the elevator is falling. That's 9.8 meters per second squared. You're accelerating, I should say, at the same rate, and so you would be like floating in the elevator because you don't, there's nothing like gravity is not pulling you into the ground. Essentially, if gravity pulling this block down is larger than this push force, then this block will be dragging this block along, which keeps the rope tight. Anyway, so what does this mean equation-wise? This means Ft is 0. So m1a equals F. And in the net force equation over here, for block 2, we had Fgx minus Ft. Again, disappears, so m2a equals Fgx. And what are we looking for? We're looking for this force, the largest force. We know m1 is 3 kilograms. And we don't know a yet, and we don't know f. Over here we know m2 is 1 kilogram. We don't know a yet. And we know Fg of x is 1 kilogram times 9.8 meters per second squared times sine 30. So A equals 4.9 meters per second squared. Just simplifying all this, which we'll then put up into here. So 3 kilograms times 4.9 meters per second squared equals F. F equals 14.7 newtons. So this is a 3-dot problem only because coming up with the fact that Ft equals 0 is conceptually pretty challenging. But hopefully you understand based on my explanation. And that is 66, and that's it for chapter 5, last video. Not too bad. Alright, see you later.